Okay, so last time on Monday I'd mentioned that our goal moving forward was to basically go in reverse to what we did in chapters 3 and 4. So in chapters 3 and 4 we introduced coordinates, right? They were brought in from outside and put on the space. And those coordinates then allowed us to prove various theorems in a different form. So we had like vector Thales, we had vector Desargs. That was, actually something that was the subject of your exam. That was one of the questions on your exam. We had vector Pappas. We had, and of course, a lot more statements than those things, but we had a lot of things that we proved using coordinates. Coordinates were extremely useful for us. They made a lot of the sorts of arguments that otherwise would have been extremely annoying, extremely cumbersome. Made them a lot easier, right? And even an aspect of it that we didn't really do that much of was, say, using coordinates to prove facts about three-dimensional geometry. So this is something that Euclid spends quite a bit of time on in the Elements. And those diagrams, as I showed you in my copy of the Elements, can get really, really, really nasty. But with coordinates, those things are much, much easier because you're dealing with vectors. And so having coordinates was nice. But it turns out that this question of can we have coordinates except not put on our space from outside? Is there something inherent about the geometry itself that guarantees us coordinates? And the answer is that in certain types of nice projective geometries, the answer is yes, there is. So the way that our approach here is going to be different than it was in Chapter 5. Is in Chapter 5 we started with the projective plane axioms. Okay, but it turns out that the projective plane axioms are not strict enough. The projective plane axioms are satisfied by some projective planes that don't have decent coordinates. So I mentioned this last time. So those there are examples of projective planes that satisfy the projective plane axioms, but they don't have a nice notion of coordinates. And we will see what goes wrong with those planes by the end of this chapter. Okay, and so our projective plane axioms are not enough. We need one more axiom, but we're gonna assume two more just to make it easy. But it turns out we actually only need one. So what is meant by this statement, geometry fights back against the forces of arithmetization, is it's going to be the geometry itself is what's going to be giving rise to these coordinates. And so we will see what these extra things we have to assume are. And go ahead and spoil in the fun. It's the Desargs and Pappas theorem. Those are the extra axioms that we're going to assume. So the point to get coordinates on our projective plane we assume both the Pappas and Desargs theorems. In addition to the projective plane axioms. So it turns out we only need one of these. We could assume either the Pappas theorem or the Desargs theorem and get the other. But we're not even going to worry about that. We're just going to assume both of them. okay, because they're both useful. They're unright. Of course, we're still calling them theorems here because the other instances in which you saw them in this course, they were honest-to-God theorems in the sense that we proved them from some assumptions. In fact, what's neat is this is exactly the opposite thing that we did in chapters 3 and 4. So in chapters 3 and 4, we defined coordinates, and we used those coordinates to prove Pappas and Desargs. And in this setting, we are starting with Pappas and Desargs theorems, and we are using those to define coordinates, as we'll see. Okay. What is cool about this is that in some sense, projective geometry is simpler than algebra. So it is somehow like more, I should say more like fundamental than algebra, and I'll make precise what I mean by that. So when I say that it is more fundamental than algebra, it's that we can literally arrive at these coordinates using less axioms. So what did we need for coordinates in chapters 3 and 4? We needed the field axioms, right? So we needed the field axioms, so the field axioms for the reals, for instance, but it didn't matter really. As long as we had the field axioms, we're good. But the field axioms, there's like 8 or 9 of those. But we're going to be able to do this development of coordinates with the 3 projective plane axioms and then Pappas and Desargs, so that's 5. It's less. We can literally do it with a shorter axiom list. So that's what I mean. Okay. All right. So to see what it is that's going on here. First, recall that we have now seen Pappas and Desargs theorems stated multiple times. So each of them, I believe, we've seen twice. And in both cases, they had a similar form, right? So what they said was that you have 2 particular pairs of lines and they're parallel, right? Then a third pair of lines is parallel, right? That's both Pappas and Desargs said that. Okay, just the configurations themselves were different. Okay, and so in this projective setting, the parallel lines actually meet on the horizon. And so the Pappas and Desargs theorems also say that if 2 particular pairs of lines meet on the horizon, then so does a third pair. Okay. And so the horizon, of course, is not different from any other line. So another way of interpreting this in the projective setting is saying that these theorems are really about 3 pairs of lines having their intersection on the same line. Okay. All right. And so let's look at the projective Pappas theorem. So first, let's look at the projective Pappas theorem. I'm not going to waste my time drawing this thing because my drawing would be bad. So I'm going to show you the very nice drawing in the book, although these lines can be very faint, so I'm going to try to get it really close to the camera. Okay. Let's see. Let's see if it will actually. There we go. Okay. So, projective Pappas theorem. 6 points lying alternately on 2 straight lines form a hexagon. The vertices of this hexagon are given by these dots filled in. Okay, and so this is, you can find this in some places called the Pappas's hexagon theorem. So that's the hexagon. Wikipedia has a nice write-up on this. There might even be like a clickable diagram. I can't remember. But anyway, so yeah, sometimes it's called Pappas's hexagon theorem because the hexagon formed by these 6 points. So anyway, what's the projective Pappas theorem says? Or say, it says 6 points lying alternately on 2 straight lines. So 3 points lie here, 3 points lie there. So they lie alternately on two straight lines, form a hexagon whose three pairs of opposite sides meet on a line. Okay, and so let's look at the three pairs of opposite sides. So there's this pair. Okay, they meet at some point on L. There's this other pair, they meet at some point on L. And then there's this last pair, they meet at some other point on L. Now, remember, this matters because you have three pairs. So let's just keep track of what's going on here. Of course, for two pairs, I get 2 points. That determines, 2 points determine a line. If you have two random points, they always lie on a line. So it's the fact that this third point also lies on the same line that's the key, right? That's the key of the theorem. So without that, you're not really saying much of anything. And this notion that you are trying to keep track of the incidences or coincidences makes this what's called an incidence theorem. So this is tracked here. Okay, so that's what the Pappas configuration looks like. Okay, in the projective setting. Now you see why I didn't bother drawing it. I feel like this is a better representation without me having to confuse you any. Okay, now what about the Desargs theorem? So projective Desargs theorem, it's similar. Okay, the statement is that if you have two triangles that are in perspective, what does that mean? So triangles are in perspective from a point if each pair of corresponding vertices lie on a line through that point. And so if I have a point P here, these two shaded triangles are in perspective if when I draw the lines through their corresponding vertices, these things, or they're in perspective from point P, sorry. If when I draw this line, those lines meet at P, okay, in this way, all right? So working in reverse, if you wanted to form triangles that were in perspective, you start with a point and draw three lines, and that gives you your corresponding vertice lines, or vertex lines. Okay, all right. And so, if two triangles are in perspective from a point, so here's the configuration I have here. Two triangles are in perspective from a point, then their pairs of corresponding sides meet on a line. Right? So here our sides are the dark black corresponding sides. They meet at this point on L. Right? Then there's the near sides, the dotted line. They meet at some other point on L, and then the very faint line, this last pair, meets at some other point on L. This is the projective Desargs configuration. Okay. Now, there's a special case of the Desargs theorem, and the special case is when the center projection is on the line L where the corresponding sides meet. Okay, so that's a special case, and it looks a little bit different. It's called the little Desargs theorem. So I'm going to show you what it looks like, and then I'm going to read what's going on here. So here's the picture of the little Desargs theorem. Okay. So our point P here, that these triangles are in perspective from, also lies on our line L, which is the line that contains the points of intersections of these opposite, or these corresponding side pairs. Okay, so what's the little Desargs theorem say? It says, if two triangles are in perspective from a point P, and if two pairs of corresponding sides meet on a line L through P, then the third pair of corresponding sides also meets on L. Right, so they're in perspective. Here's my point P. Two of them meet through on points on L. The other one meets, the other pair also meets on L. And of course, it didn't really matter which two pair I took, right? The point is that it's the last pair out that's determined there. That's what the theorem is saying. Okay. All right, and so we have a thing to say now. So we take the projective Pappas theorem, the projective Desargs theorem. Little Desargs is a consequence of Desargs, so projective Desargs theorem. And little Desargs. We'll discuss at the end of this chapter why there is a reason to make any distinction at all. But what we can do is projective Desargs actually, so little Desargs, since it's a special case, what we do is we assume these two. Okay, so we assume projective Pappas and projective Desargs theorems, and we take these as new axioms. So new axioms. We take this plus projective plane axioms. Okay. So this gives us a type of projective plane called a Papian plane. So a Papian plane is a projective plane such that Pappas's theorem holds. It turns out that if that's the case, then Desargs theorem also holds. So, so a Papian plane is one that satisfies the projective plane axioms together with the projective and Pappas and Desargs theorems. Okay. So what's an example of a Papian plane? RP2. So RP2 is one such plane. Okay. And so this this quest that we're on to put coordinates on our space is going to be successful for RP2. Okay. So this is going to be successful for for RP2 because it is the right kind of plane. Okay. Why is this nice? So as I said, well, it turns out our old way of putting coordinates on a space required all the field axioms. So you can refresh your memory. We went over this in chapter 4. We went over the list of field axioms. And it was actually kind of annoying because, for instance, if you remember, I made the the point to mention that technically, if you went through all your rules of linear algebra that you needed to in chapters 3 and 4 to do all the Euclidean stuff, it wasn't technically as efficient as Hilbert's list of axioms for Euclidean geometry, meaning that you needed more axioms technically. I think you needed like 2 more axioms than Hilbert used. But the benefit was that the algebra axioms that you needed, one, most of them were simpler than Hilbert's axioms, and they're also broadly useful. Whereas Hilbert's axioms are a lot more narrow. They're something that basically you're only going to come across in that context, whereas the other stuff is broadly applicable in linear algebra stuff. Okay, so yeah, so it turns out that this required all the field axioms from chapter 4. So there's 9 of these. So 9 of these, depending on how you group them. I guess used to there was 10. I guess you could group 2 of them. You could. That's right. Yeah. So there's 9 of these. There's 9 of these, but we will be able to do this. And we will be able to reproduce this using only 5 axioms. And the 5 axioms in question are the ones up here, right? So 3 projective plane axioms plus Pappas and Desargs, which is pretty awesome. Okay. It's also not really immediately clear, just like when you see, the projective plane axioms, Pappas and Desargs theorem, is just not at all clear why this would do it. So that's what we're going to be doing for the rest of the chapter. Okay. All right. And so, what we want to keep track of is kind of the only thing we can keep track of in projective geometry, which is coincidences. And of course, this actually is true in the English sense too. So, what is a coincidence? Well, if you have 2 points, then they always lie on a line, right? 2 points determine a line. That's one of the axioms. So 2 points always lie on a line. But then it is, accidental if a third point lies on the same line, right? That is a coincidence if that occurs. Okay. And so keeping track of coincidences, right? When objects coincide that there's no reason to expect that they should coincide, keeping track of coincidences is kind of the only thing you can really keep track of in projective geometry, right? You can't keep track of length because you have no compass. And so, I should say you can't directly keep track of length, but we're going to see that we can actually reproduce. I mean, we're going to need to reproduce that essentially if we want to be able to put coordinates on this space. And so a coincidence is 2 incidences together, right? So coincidence, this is 2 incidences together. So in that example, if I have, points A and B, well, as we said, these things always lie on a line. Okay, so 2 points always determine a line. But then if a third point C also lies on the line, that's the coincidence. So there's 2 incidences. There's the incidence of A and B lying on a line, and there's the incidence of C lying on that same line. All right. All right. And so that's essentially what Pappas and Desargs say, is that certain coincidences occur. And that's exactly what we can track with them. And to see an example of how this works, I want to refer to that. So again, this is going to be me not writing that much here and looking at the book because because the picture will be a lot clearer. So if I look here, I want to refer to this old construction of a perspective view of a tiled floor. Okay, and so, for instance, if we start and we've marked off our first tile here however you wanted to, so that can be completely arbitrary. Then if you draw this first line, so of course this is going to be one of your construction lines, so you're going to erase this to make everything look nice. That's why it's drawn in a little bit lighter, if you can see there. So so I draw in this first construction line very lightly. Okay, and once I do that, I can make a choice here, right? I can either draw in another line, either connecting this or this. So the way that it's done, we always pick the left point. So, okay, so we connect this with our other construction line. So then what do I do? Well, where this actually intersects, say, this line, now I can extend another line from infinity, from the horizon through that point. So this gets me the beginnings of my second row of tiles, and I continue on like that. But at this step is where a coincidence happens. So what do I mean? So I've gone through this entire process, and why am I saying that the first place that a coincidence happens is here? So what is the coincidence that I'm talking about? So it is in filling this out that if you actually were to fill in this other construction line, so for instance, at this point, so it's filled in here below. So 3 of the points that we've constructed lie on a straight line, which is shown dashed here. So basically, here is the line that it is a coincidence that this line fits in this way. Okay, so then why does this happen? Right, why does that coincidence happen? Well, it turns out this coincidence is a consequence of the little Desargs theorem. And to see that, you have to look at this diagram. So this is a special case of little Desargs theorem, which involves these two shaded triangles here. So let's see why this is. So if I draw in these two shaded triangles in this way, okay, and so these triangles are in perspective from this point P. The reason it's little Desargs now is because the point they're in perspective from is my point, is my line at infinity, or my point is on my line at infinity, where these these corresponding side pairs meet, right? Okay, so since we have the little Desargs configuration going on here, what we get is that these double tiles here actually meet on the horizon. So that's what I get in this picture here. It can be a little bit confusing, so that's why I'm leaving this on the camera for a bit. So you should pause this and read through it on your own. But this is exactly what it is that's going on. Okay, and this is one example of how you can use either Pappas Desargs or little Desargs to explain a coincidence or keep track of a coincidence involving points, and figuring out which of these things lie where you think they should. Okay, and so there's a few more things before we are able to continue on, before we can actually define the projective arithmetic that allows us to talk about the coordinates that we want. I have to discuss a few variations of the Desargs theorem. So one is the Converse Desargs theorem. So what's the converse Desargs theorem? So if corresponding sides of two triangles meet on a line, then the two triangles are in perspective from a point. Okay. So how do we prove this? Oddly enough, this is actually equivalent to the Desargs theorem. And to see this, I'm going to show you the following diagram. So suppose we have the following diagram. I have a line L, and I have this statement that I have two triangles. Corresponding sides meet on a line, so I've paired them up in a way that all of these, I know some of these are a little bit light, so I'm trying to get in close to the camera here. So all of these corresponding sides meet on this line L. Okay. So all the corresponding sides meet on this line L. And what I want to do here is, in this picture, I want to use this labeling here. So ABC for this triangle, A prime, B prime, C prime for the second triangle. And then I have this point C double prime. Now, this has been drawn in the diagram specifically so that C double prime and C prime are not equal. So it's drawn intentionally so they're not equal. But I want to show that this type of situation can't happen. Okay, so I want to show that this can't occur and that actually C double prime has to be C prime. Okay, and so maybe I should put this diagram here and continue writing. I think that would be nicer. Maybe I should do something like this. Let's see if the camera will adjust. There we go. Okay. And so, how does this work? So here's what my picture looks like. So the proof then is to let ABC and A prime, B prime, C prime be two triangles whose corresponding sides meet on L. Okay, as depicted here. Okay, so let P be the point of intersection of the extended line segment A prime, and B prime. Okay, so here's A prime, B prime. They meet at some point. We call it P. Now the idea here is that it's this P that I hope to show these triangles are in perspective from. Okay, and this is going to work so long as in this setting, the C double prime is actually equal to C prime. Okay, so I want to show that P lies on C prime as well. Okay. Oh, I'm a little bit off the page there. There we go. Okay. Well, we suppose that PC meets this line B prime C prime at this C double prime, right? So if it's equal to C prime, we're done immediately, right? So suppose this is how we construct the C double prime. So suppose that PC meets the line B prime C prime at C double prime. Okay. Okay. All right. Then forget about the shaded triangles for a second. Then the triangles ABC and A prime, B prime, C double prime are in perspective. So they're in perspective from P. So by Desargs, their corresponding sides meet on a line. But we already know that AB and A prime B prime meet on L, and BC and B prime C prime meet on L. So what this means is that AC meets A prime C double prime on L, right, at Q, this point labeled here, and this is where AC meets L. Okay, but then Q A prime goes through C double prime. All right. But QA prime meets B prime C prime at C prime. Right, that's literally how this is defined. Thus, C prime is equal to C double prime. And that's it. So these triangles were actually in perspective from P as required. Okay. Okay. All right. So that's one variation of the Desargs theorem. We need another called the Scissors Theorem, which is a pretty funny term. So the Scissors Theorem is called the Scissors Theorem because two of the the pictures that you draw here, the figures look like a pair of scissors. That's why it's called the Scissors Theorem. So I don't know that this is actually the standard name of this fact, but it's useful for us going forward in defining this arithmetic. So this is also equivalent to the Desargs theorem. So what does the Scissors theorem say? So if A, B, C, D, and A prime, B prime, C prime, D prime are quadrilaterals, with vertices lying alternately on two lines, and if AB is parallel to A prime B prime, BC to B prime C prime, AD to A prime D prime, then also CD is parallel to C prime D prime. Now, that being drawn in this way, this means absolutely nothing to you. Just looking at it like this. And so, what does this actually look like, and why is it called the Scissors Theorem? So here's why. Look at the quadrilaterals involved. They look like a pair of scissors. Okay, so here's one pair of scissors, and here's another pair of scissors. And the pairs of scissors are in perspective in this way. And what this is saying, and it's kind of hard to see because there's so many different things here, but it's saying that if the solid lines are parallel, so AB and A prime B prime are parallel, and the dashed lines are parallel, BC and B prime C prime, and the grade lines, so AD and A prime D prime, are parallel, then also these dotted lines, so CD and C prime D prime, are parallel. Okay. What if you mix that up, right? What if the black, gray, and dotted lines are parallel? Are the dashed lines parallel? And the answer is yes. It just changes the picture a little bit, but the proof is basically the same. It's very similar reasoning. And so we can actually prove this by the Converse Desargs theorem. So I'm not going to go through this, but this is on your textbook. So proof is by Converse Desargs. So this is page 126 in your textbook. Okay. All right. Okay. And so we are almost ready to begin projective arithmetic, but we'll start on that next time. So we'll start on projective arithmetic next time, so we're almost ready to define it. Just needed to tidy up a few last minute things. Okay. All right, so I think that's it for today, but anyway, so we'll tidy this up next time. So I will see you all soon.